So, welcome and thank you for your kind invitation to give the keynote for this wonderful conference. Thank you for the organizers for inviting me. So this talk is about getting the magic combination of productivity, so time to solution for actually getting computational science done is what's on my mind, performance, and performance portability, meaning that we can take essentially the same program and run it on a machine perhaps with a different accelerator or a different architecture and get pretty good performance direct out of the box without further manual hacking. And I'll show you during the talk a couple of examples of where I think we've really achieved that. I'll also talk about some of the problems we have in pushing that solution. So this is all about domain-specific optimizations, right? It's about tools that automate code generation for particular application domains, starting from some higher level representation. And there are good reasons why people are resistant to domain-specific technologies, which we'll come to later in the talk. And I'll talk to you a little bit about what I think is the way forward to resolve that and to enable this approach, this domain-specific code generation approach, to work across a much broader range of applications and to get much more uptake in application user communities. So this work is the work of many, many other people, some of them because they led the projects I'm going to talk about, some of them because they did the actual work and produced the graphs that I might show, and some of them because they simply inspired me or helped me understand or think about some of the things I'm going to tell you about. So let's start with this. Who am I and what do I do? Well, I'm a professor at Imperial College and I teach compilers and computer architecture. I've been doing lots of different kinds of computer systems research over the years, but one of the things that I'm proud of is our work on pointer analysis for general purpose compilation. In fact, our work was adopted into the GNU compiler collection. When I say our work, I mean the work of my PhD student, David Pierce. The fact is that the benefits of that were not exactly revolutionary. And whilst I have every respect for, and I'm very happy that there are people around the world trying to make our compilers for general purpose programming languages better, I wanted to do something which makes a bigger difference. And so I found myself working with application specialists who knew that there are major performance optimization opportunities in their code. Often they spend a long time manually implementing those optimizations. And so I got interested in automating them so that you can, for example, modify the PDE that you're actually solving and automate the generation of high performance code using all the tricks that you know in order to be able to run it fast. So this talk is about domain-specific languages. It's about getting from using general purpose programming language tools, the Swiss Army knife that I've shown here, to finely honed tools for particular tasks that can be immensely more productive and efficient. What we want to do is deliver domain-specific optimizations by whatever means necessary. So I'm actually not completely tied up on the language thing. If it's a library or something like that, that's fine with me. What matters is that we have some means by which we can deliver domain-specific optimizations and automate the implementation of sophisticated and important transformations. And the other thing you want your domain-specific code generation tools to do is to collect, is to form a repository of all the things you know about this family of problems and how to solve them fast. And if we get it right, as I promised with the title of this talk, we get productivity by generating low-level code from a high-level specification. I'll show you examples of that. We get performance by optimizations often, and when you're doing this well, you're automating optimizations which are really hard to do by hand. And we have some really good examples of that. There are many, many research papers where people have manually hacked high-performance code. What we want to do is automate it and reuse that effort for multiple problem instances. Performance portability is because we potentially hide the details of how to restructure your code for a GPU or FPGA or some other accelerator, vector instruction set or something like that. We hide all that from the very high level specification of the problem. And the most important thing, the really big story, and if you hear nothing else from me today, this is it. If you can raise the level at which computational scientists think about, understand their problem, model the physics of what they want to do, design the numerical methods that they want to use, if you can raise the level so that you're really harnessing their expertise and automating the pathway, what you want to tell them is, I'll take it from here. I'll take it from here so you can concentrate on the big stuff. Because basically, compilers, computer architectures, we can make interesting, important performance differences, but nothing compared to the science delta achieved by solving the right problem using the right method. Okay, so I want to tell you this, that compilation is like skiing. So this is a ski map of the Matterhorn, and in the middle we have something that I tell my undergraduate students studying compilers, that compilers have two halves, an analysis half and a synthesis half. The analysis half is where you try and understand what the programmer wrote. So it starts with syntax analysis, but it goes all the way through to dependence analysis. Along the way, we do the pointer analysis that I mentioned. We might try and understand the call graph, the call hierarchy, the class structure, and all of that. And there's an immense body of virtuous, exciting, mathematically sophisticated engineering and science involved in doing all this. But when you've finished, what you've done is you've built a representation of everything that you know about this program. And from there, you should be able to generate code. And one of the kind of big discoveries in compiler research over the last couple of decades, actually, is that there's at least as much fun to be had in figuring out what code you should generate, given that you know everything about the starting point. So if we could just start from a higher level language, we can move up and capture more about the problem space. And if we use domain-specific languages, we might even have the chance to take a helicopter to the top and not do all this boring stuff, not carry your skis up the mountain, and instead take a shortcut. So the plan for my talk today is compiling is like skiing, analysis is an uphill struggle. Let's try not to do it, and instead think about designing representations that make analysis redundant and optimization and code generation easy. An analogy that I find helpful with this is the Turing tax. So I don't know how, I heard about the Turing tax from somebody else, and I've been talking to lots of people about it because I rather think it's an interesting idea. I've made a video about it on YouTube if you're interested. It's the price that you pay for running on a general purpose computer instead of building a specialized ASIC for your particular problem. Right? So it's kind of the price to pay for the von Neumann model. It's the fetch execute price to pay, for example. And there are many other ways in which we pay an interpretive overhead in a computer when you could have designed a specialized machine. My question for today, though, is what about this? What do you call the price that you pay for using a general purpose programming language rather than a finely honed domain-specific tool? I've been struggling to figure out what I should call this. Is it somebody else's tax? I'm not sure. But it's a thing to think about. It's often something that we kind of assume is not the issue. We find ourselves recoding in a low-level language in order to get performance. Actually, I think we should be looking for the opposite. So this talk, I will try and show you that DSLs really can deliver. I'll show you a couple of the examples that I present to make that point and hopefully prove it. I want to, towards the end, synthesize something about how domain-specific optimization really focuses your mind on compiler architecture, on finding the representations that make your optimizations easier. And that leads to the kind of something I'll mention at the end, because it's work in progress and very preliminary from our point of view, is trying to fix the domain-specific language ecosystem by building common compiler infrastructure that might span multiple domain-specific language projects. Okay, so that's the proposition that carrying your skis uphill, doing all that analysis, is all a kind of tax that we should aim to evade or avoid. Sometimes I prefer to call it Turing tariffs rather than Turing taxes, because that seems like something more that you should avoid with a clearer conscience. So let me show you the first example. This is a project called Firedrake, and I will try over the next few slides to answer some of these questions about what this thing is, what its domain-specific language actually looks like, what it's good for, what its compiler looks like, does it actually generate good code? And we won't have time for all of these questions. So here's the webpage for the Firedrake project, and here are the people involved. And I should point out that although I was there at the beginning, the project is led by David Ham and Lawrence Mitchell, and it's a collaboration that combines compiler technology with applied mathematics. And my experience as a compiler person has been to constantly live at the kind of boundary between what I think I know about in terms of code generation and the mathematics of what's going on, which I honestly don't fully understand. Luckily, they keep on talking to me so far, and it's been a productive partnership. So Firedrake, I'll tell you a bit about Firedrake itself. I wanted to first talk about what it's used for, and what happens is that people build tools on top of it to do particular kinds of science. For example, Thetis is a tool for unstructured grid coastal modeling, so ocean modeling, sea around the coasts of Britain and other places. Let me just show you what that's actually about. This workshop is virtually located in Bristol. Bristol is next to the Severn estuary, this river, and because the oceans around us are very tidal, there's an enormous tidal flow that goes up and down this estuary every day. And so it's been proposed that we should use this to exploit, to generate electricity, perhaps even by building a barrier right across. I understand that this idea has been discounted because of the massive environmental impact that it would have. But one of the things that was done with Thetis is to try and evaluate different designs and their energy potential. In fact, also potentially their pollution or their environmental impact as well. So that's Thetis that uses Firedrake. Firedrake has also been used for prototyping the new numerical methods for the next generation of weather simulations for the UK Met Office. And one of my favorite collaborations is because they just found us on the web and picked up the tool and started doing stuff, is this project on glaciers. So what you see here is streamlines of flowing ice. So Firedrake works, so it's a tool for solving partial differential equations, particularly used in geophysical flows, but not only. And what it does is it automates the finite element method. So the finite element method is only one of a number of numerical method or structures, mathematical frameworks for solving PDE on a computer in a discrete and finite way. Very roughly, the idea is that we've got some PDE that tells us about the behavior of a continuum. To solve it on a computer, we have to find a way to divide the continuum up with some kind of grid. In this case, it's an unstructured quad grid. And what the PDE basically does is expresses conservation laws that must hold between the adjacent cells. And in order to solve the equation, what we need to do is to compute integrals along the edges of these cells, and from there derive couplings between the cells and construct a system of linear equations to represent those couplings, which we then solve to compute the state of the flow of the fluid at a given time step. So what we're doing is we're trying to find a way to make a continuous thing finite with a mathematical framework based upon a theory that tells us how to evaluate the state of the flow at any given point using an interpolation, perhaps, and a polynomial interpolation across the body of fluid inside the cell. So what we do is for each cell, we construct a local matrix representing the integrals that we calculate. We can then insert that into our global system of equations to create both a left and a right-hand side. This is a large, sparse matrix. You don't necessarily have to construct this matrix. We very commonly use matrix-free methods where we repeatedly do the assembly rather than assemble once and reuse the matrix, because the matrix can be very big. So the structure of Firedrake is firstly the local assembly part, which is roughly where we weave together the differential equation we're solving and the specification of the discretization that we're going to use to solve it. We apply that at every triangle, so there's a parallel loop structure to loop over the mesh. And then we need to think about how we're going to solve that linear system. And we call out to standard tools using PETSI, which in turn call us back, for example, to implement a matrix-free solution scheme. So the next question you might ask is, so what does this domain-specific language actually look like? Well, let's begin with a tutorial from the Firedrake website. And there's some maths which we don't need to concern ourselves with too much at this time, but what we get is the weak form of the partial differential equation, this expression here, which needs to be equal to 0 for the equation to be satisfied. And basically what you do with Firedrake is you transcribe that thing into Python. So un+1, so un+1 is u here, and u underscore is the previous time step. And what we have here is basically an ASCII version of the expression that we have up there. Having constructed this thing f, we know it's supposed to equal 0, so we set up that equation and solve it for u, given that we know u underscore the previous time step state. And at that point, Firedrake generates code to assemble a linear system, it runs the code, calls the linear solver, and you can start looking at the result. So here, just to emphasize that, I picked this example because it's a simple one. The code on the left is the entire example, and the key line is this one, the one where we set up the PDE, which came from the previous slide. Let me just go through that in a little bit more detail. So what we do is we construct a mesh, for example, a unit square mesh of triangles. We construct function spaces on that mesh. In fact, this one uses linear interpolation, so it's polynomial order 1. And this we're going to use for actually outputting the data. We're going to solve the equation on a mesh with polynomial order 2. So on these function spaces, we have variables. We have the velocity variable. We set up some initial conditions. We don't need to look at that now. Here's the equation that I showed you. And here's the time-stepping loop. So in each time step, we solve the equation for the next state. Then we update the current state, iterate, and write out a snapshot each time, interpolating onto the linear interpolated mesh. So that's a complete example in Firedrake's domain-specific language. As you might have spotted, this is Python, so the DSL is embedded in Python. The code that it generates is in C. Here's, from a very great distance, one example of one of the operators that are generated in C for you. From this distance, you can't see the code. The important thing is that it's quite complicated. It has quite complicated loop structure. It actually started as a rather simple loop nest, but then we went to work on it in the compiler and we lifted expressions out in order to remove redundant re-evaluation of expressions in the code. We also went to some trouble to achieve vectorization. So there are many optimizations in Firedrake, and I don't have time today to tell you all about them. The question you might ask is, do they add up to decent performance? Well, I would claim yes. One of the wonderful things about working with a domain-specific language is that you get to see how your optimizations play out across a whole space of possible of example problems. So we have different example problems here being solved with triangles in 2D, quads in 2D, tets and hexes in 3D, using a range of polynomial order from all the way up to polynomial order 6. So we get many points here, and we can see how it plays out. And often, we really are actually achieving something close to the theoretical peak or the practical limits of what the hardware is capable. So for some of these problems, we hit a memory bandwidth limit. Some of these problems, we hit the flop limit. We're not limited by memory. Sometimes this is because the numerical method, the particular combination is not very sensible. It does more flops than it needs to, and that's how we end up in points like this one. There is room for improvement. There are some cases where we're not quite there yet. So how do we get there? Well, we built a compiler. In fact, we evolved a compiler over some years. And one of the things I wanted to emphasize in this talk is, so compiler architects for LLVM or GCC or other compilers for general purpose programming languages, they do think about the intermediate representations of their compilers, and they do think about progressive lowering. For example, they start with a representation that has explicit, has array subscript expressions, for example. So a multi-dimensional array actually looks like a multi-dimensional array, and then there's a lowering step that turns that into pointer arithmetic. That kind of thing happens a lot. In domain-specific compilers, something on a grander scale could be happening. So in Firedrake, we have a polyhedral representation of loop nests. We have a abstraction for iterations over unstructured meshes, which makes explicit all of the dependence information, and that enables us to do all sorts of optimizations, including, for example, tiling for unstructured meshes is one of the things that we've explored. That code actually comes from a higher level representation. It's a tensor contraction representation. And that's where a lot of the algebraic simplification of the resulting code comes from. And that is the target for what you might think of as actually the domains. This is where the DSL is mapped into an abstract mathematical representation in the compiler. So this language UFL, actually we didn't invent it. We borrowed it from another project called Phoenix. So there are now 2 implementations of the same domain-specific language, more or less. So incidentally, all of this is in Python. All the code that actually touches real data is in C, and it's generated at runtime. We cache the compiled code, so you don't recompile code unnecessarily. And you can cache the code and then distribute it to large supercomputers if that's needed. Firedrake's compiler architecture has evolved actually over a period of time, and here's here's one of the evolutions that I think is instructive. We did a lot of work on vectorization, And during that work on vectorization, we discovered that there were loop invariant expressions that we wanted to eliminate, but they were not being eliminated when we simply output the code into the C compiler. Even the best C compilers, none of the C compilers we could find, will lift invariant expressions out of a loop if the expression is variant in an enclosing loop, but nonetheless redundantly computed because of loops outside that, so non-innermost loops. So that generalized loop invariant code motion was implemented here as part of our vectorization work, and then later it was lifted out and abstracted to an algebraic representation of the code. And what was particularly wonderful was just how much code we got to delete when we did that. It just got so much simpler. And it was a real object lesson in how getting the representation right, introducing this tensor contraction representation, really, really helped. Okay, that's Firedrake. The other project that I wanted to talk about, I'll talk about a little bit more briefly, is called Devito. And it's a sort of spin-off. It came from people who were watching what we were doing with Firedrake and wanted to do something similar for finite difference method instead of the finite element method. So I'm going to try and answer some of the same questions quite briefly. Firstly, here's the homepage for the project and some mugshots of the people who actually lead it. So there are many people involved in the project, but Fabio Luperini, who used to work on Firedrake, is the lead engineer, and Gerard Gorman is an academic in earth sciences at Imperial who runs the project from a higher level. Devito automates the finite difference method, and so finite difference is widely used for fluid dynamics. We mostly are driven by wave propagation problems, and in particular, we're interested in inversion problems. So this is where you perhaps have some kind of wave propagating through a medium, perhaps rock, or perhaps a part of the body like the brain, and you have microphones that receive either transmitted or reflected signals through the medium. And our job is to try and figure out what the medium is, what's in the ground, what's the geology, or what's going on in your brain. And that leads us to solving inverse problems, which require automatic differentiation. Automatic differentiation is made much easier by working at a higher level representation of the computation. We don't automatically generate the low-level implementation code. We can automatically generate at a higher level in the compiler. Here's a concrete, simple example. So this is about the acoustic wave equation with some damping. Here's the PDE with some boundary conditions, but this is the PDE itself. Here it is again transcribed into Python. And again, we basically use this to solve for the next time step in a similar way that we saw in Firedrake. So what's happening here actually is we're not solving directly, we're constructing a time-stepping operator. This is one part of the time-stepping operator. The other part of the time-stepping operator concerns injection of the sound waves, and we need to figure out what to do with the receivers as well. We need to interpolate what we expect the receivers to receive. So we construct a composite operator that combines all of those things, and then we can run it for some number of time steps and predict what the receiver will actually pick up. So this is slightly simplified from an online tutorial that you can go and look at. Basically, code written at this level of abstraction is being run in production, at scale, in the cloud, for profit, at multiple petaflops, like 10 petaflops roughly, 24/7, non-stop. Do we generate decent code? Well, we worked pretty hard on it. Here's a classic roofline diagram. Actually, the point of this roofline diagram is to show that the roofline isn't always the whole answer. So the red data here shows before the more sophisticated optimizations are turned on. And the green shows what happens when we turn all the optimizations on. And what happens when you turn the optimizations on is that the flop rate goes down. The good news is that the time to solution that you see here gets better. And the reason is because our optimizations actually remove flops from the calculation. So a big part of that compiler architecture is to identify redundant expressions and avoid calculating and recalculating them. Another thing that we're working on with Devito is tiling in time. So we're trying to reduce the total memory movement, data movement of the problem. So try and break through that memory roofline. What you see here is, for example, the triangles here are for a relatively low space order 4. And tiling, so tiling in time means grabbing a patch of the data and progressing multiple time steps on it before moving on to the next time step. And as you can see, this potentially offers quite big performance advantages. For higher spatial order, for higher polynomial order, the win gets smaller, essentially because these are more flop-intensive calculations and less dependent upon the memory movement. Here's the promised compiler architecture, and I won't spend very long on this. The main things that we're proud of in this concern that flop reduction work. So finite element stencils often lead to repeated terms. We want to try and factorize those expressions in order to minimize the redundant re-execution at each point. You can then also look at expressions which are common between adjacent points, and we work on exposing those expressions too by not just searching for them, but trying to generate them by doing algebraic manipulation like exploiting distributivity and so on. We obviously also do blocking, we do spatial blocking, and in prototype form we have temporal blocking as well. We do vectorization, we do shared memory, hierarchical, and MPI. So I've been talking for a long time, and it's time to try and pull some of this together. So what have I learned? I've learned that engaging with applications can be really, really fruitful. Learning about what people use your tools for and what optimization would really make a difference to them is incredibly valuable, and it provides a fantastic way to get beyond incremental research. I've also learned that compiler architecture is much more fun in the domain-specific context, and designing the right representations is a real art form. So what we do is we construct or try and capture the highest possible level of representation of the problem, and then successively, progressively lower it to something which exposes low-level optimization opportunities, and then finally, we actually generate code. And premature lowering is what that architectural change was about that I mentioned in Firedrake. Premature lowering is where you lower and then you discover that you've lost structure that you need to try and recover. And this is where you find yourself carrying your skis back uphill again. And if you can avoid that, then you're winning. And of course, along the way, we might hope that we learn something about general purpose compilers and perhaps some of the general programming abstractions that we should look for. A good example of that, I think, is tensor contractions, actually, and also computations on unstructured meshes. So the other thing that I promised in my talk today was to say something about domain-specific languages and why you shouldn't use them. So users have really good reasons to ignore everything that I've said today. For example, they're going to ask, what about, will your domain-specific compiler tool outlive my project? So we have this in a big way with the project with the Met Office, where they're trying to design a software infrastructure for a 20, 30-year time frame. And they didn't completely believe that our tools would be around in that time frame. They're very committed to basically, depending on only things they completely control. So the question is, how do we persuade users that there's a long-term ecosystem on which they can rely? The walled garden problem is another one. Suppose that I buy into this domain-specific language idea because it solves the problem I have today, and then I discover a little while later that there's something I must have that your DSL doesn't support, and suddenly I'm really stuffed. And if I just rolled it myself, I could fix that. What I hope, of course, is to fix it by fixing the DSL implementation and join us in doing so. We have collaborators who do exactly that. Another one is interoperability. Very often the part of the solution that the DSL handles is only part of a larger system. And we need to make sure that you can connect the code the DSL generates and the data structures that it uses into the rest of your code base. A kind of symptom of some of the problems in the ecosystem is also this. Devito and Firedrake share philosophy, but no code. In fact, if you look at a very profitable and common area for DSLs is stencils, like what Devito does. And I tried to make a list this morning of projects or code bases that implement DSLs for stencil codes. And none of these projects share any code. They're all complete standalone silos of implementation. And that is a problem, I think, and something we should aim to transition away from. And that brings me to the end of my talk with this, which is a project that we're just starting. It's a collaboration with friends and colleagues at the University of Manchester and Edinburgh Parallel Computing Centre. And the proposition here is that MLIR is the answer. And we'll tell you whether it really works out. Actually, we don't have enough money to make this revolution really work. So I would most love it if you join us, actually, and help deliver domain-specific language or domain-specific optimization components as MLIR dialects as part of a solution that can be supported by a community. So MLIR is the multi-level intermediate representation. It comes from the people who brought you the LLVM compiler. And it's a way of capturing higher level representations or domain-specific semantics, or so you can use it either to represent problem-side DSLs, or actually you can also use it to represent how your code has to look if it's going to run on a GPU, for example. And the philosophy is that you do progressive lowering, as I was telling you. That what we do is we map our source code DSL into an MLIR dialect and then progressively lower the MLIR code through a sequence of MLIR dialects, each of which is amenable to optimisations that exploit what we know at that level. And the proposition is that MLIR is supported by a lot of industry people, particularly because it's a central plank in supporting deep learning accelerators, for example. And so there's really an opportunity to hook into that ecosystem and solve some of those dysfunctional ecosystem problems we have with domain-specific languages in computational science. So I hope that you will get in touch with us and join us in making that work. Okay, that brings me to the last couple of slides. The real value of these high-level DSLs is not really in the performance that we achieve. It's that we liberate the users to explore their own design space. We enable them to navigate their world using their expertise, knowing that we will look after the rest. Firedrake automates finite element, Devito automates finite difference. In the future, I would like to think that we will have some automated pathways from math to code for many classes of problem, and that these will interoperate, and so we can build hybrid and coupled solvers, thanks to working on common software infrastructure. And finally, let me tell you this. We get used to the idea that you can program in a very, very high level language, but if you want performance, you're going to have to recode in a low level language. I want to tell you that every time that happens to you, you should feel robbed, because your high level language should be feeding your compiler, perhaps your domain specific compiler, information that will help it generate better code. And program generation tools, program generation use starting from a domain-specific representation, is how we do it, how you get to have your cake and eat it too. Thank you very much indeed, and look forward to your questions.